Chapter 1, Section 3. Now that we've talked about linear functions, we can move on to look at functions in general. A lot of times we would like to know how fast a function is changing as you move. How to measure that is by letting x increase a certain increment every time and seeing how the y value changes. From that, we can make statements about the rate of change of the function. Rate of change is how fast the y values are changing in general. So if gas goes from $2.30 to $3 over a 1-year span, the rate of change is 70 cents a year. If the data is linear, this rate of change is just the slope of the line, but many times it's not linear. We'll look at cases of all different types of functions. We're going to find the average rate of change, which is what we'll be mostly dealing with in Chapter 1. We can look at functions that are linear or nonlinear by using the function formula. F of b minus f of a over b minus a. This is a response to change in y over change in x. Now f of b minus f of a over b minus a is a formula that we'll use quite often and might be worth writing down. Again, this formula is used whenever you see that you want to calculate the average rate of a change. Well, what do b and a mean? You're going to be given x values to look between on a function. So for example, you might be looking between x equals 0 and x equals 5, or x equals 3 and x equals 10. It'll change depending on which situation you're looking at. But these numbers for x are going to represent your a and b, where b is going to be the bigger x value that you were given, and a is going to be the smaller x value. And again, f of b and f of a just means that we'll be plugging those numbers into whatever function we're working with. Well, let's look at an example to see how this all works to find the average rate of change of a function. So in general, you'll be given a function and you'll be given x bounds. Here we're looking at the function y equals x squared between x equals 2 and x equals 5. Now, like I said before, b is the bigger x value. So here, b is 5 and a is the smaller x value, which is 2. Our formula, f of b minus f of a over b minus a, will now become f of 5 minus f of 2 over 5 minus 2 by applying our definitions that we just looked at. So what is f of 5 and f of 2? Again, that means we're taking our x value and plugging it into our formula, our function, to get out a y value. So f of 5 means we'll plug 5 in to the function x squared, so 5 squared is 25. So f of 5 equals 25. f of 2 means we'll take 2 and plug it into the function. 2 squared is 4. So our formula now looks like 25 minus 4 over 5 minus 2. Well, that reduces to 21 over 3, which is 7, which means the average rate of change of the function x squared between x equals 2 and x equals 5 is 7. Let's look at another example to make sure we have this down. If we want to find the average rate of change between x equals 4 and x equals 7 of the function y equals x cubed minus 2, we want to do the same steps we did before. Step 1, we can calculate f of 7 and f of 4 because that's what we're going to have to use in our formula. f of 7 means take the x value of 7, plug it into your function, which gives us 7 cubed minus 2, which is 341. f of 4 means take 4, plug it into your function of x cubed minus 2, which gives us 4 cubed minus 2, which is 62. So plugging this into our average rate of change formula, which is f of b minus f of a over b minus a, will give us f of 7 minus f of 4 over 7 minus 4, because again, the bigger number was 7, the smaller number was 4. Applying what we've calculated, that equates to 341 minus 62 over 7 minus 4, which equals 279 over 3, which is 93. So the average rate of change for the function x cubed minus 2 between x equals 4 and x equals 7 is 93. What does a rate of change look like? What exactly are we finding? Well, the average rate of change is represented by the change in y over the change in x, which is a line called the secant line. So here, if we had 2 points, 2 x values, we would look at the graph and draw the line that would connect those 2 points. That's called the secant line. The slope of the secant line that connects the points by A and C is the average rate of change. This often gets applied to physics, so we'll look at the application that it has. So in physics, distance is defined to be how far an object moved. For example, 5 feet, could be 5 meters, could be 10 kilometers. It's just the distance of how far something is moved. Speed in physics is how fast something moves. So for example, 45 miles per hour. Speed is always going to be positive or 0. Velocity is very closely related to speed because velocity is speed but with a direction. So now you can move in a positive direction or in a negative direction. So if you were to walk backwards, that would be taken into account. Now there's a relationship between some of these things where velocity is distance over time. So if you know the distance of how far something is, say it's 60 meters, and the time it takes to travel that distance, say it takes 4 hours to go 60 meters, then you can find the velocity by doing distance over time. So 60 meters divided by 4 hours is going to give you a velocity of 15 meters per hour. Now this will come up frequently throughout the semester where we'll just be using things like this, so this relationship is sort of important. So velocity equals distance over time is a good thing to try to remember. Let's say we want to take our physics example and look at it in a table. A lot of times in physics, they use actual data that they've calculated from running an experiment, so a lot of times the data is presented in a table. So let's say this table represents a mouse running in a straight line, where we can look at the information about the average rate of change and the average velocity all at once. So at time 0, the mouse has gone 0 inches. He's right at the starting line. After 2 seconds, he's gone 120 inches. After 4 seconds, he's gone 260 inches. And after 6 seconds, he's gone 390 inches. So if we wanted to find the average rate of change over the entire experiment of 6 seconds the mouse was running, we would use our f of b minus f of a over b minus a formula, where our bigger number would be 6, that's the end time, and our smaller number would be 0. So we would be looking for f of 6 minus f of 0 over 6 minus 0. So here, f of 6 is 390, minus f of 0 is 0, divided by 6 minus 0. So 390 divided by 6 is 65. So the average change is 65. But here, we have y units and we have t units. Our y units are in inches, and the t units are time. So the actual average rate of change is 65 inches per second. So the y unit over the t unit. This is the distance over time, so it's not only the average rate of change, it's also the average velocity. So here again, the average velocity for this mouse in this experiment is 65 inches per second. Another thing that comes along in this chapter talks about different types of graphs, because as we start graphing things and looking for things like average rates of change, we want to be able to talk about the graphs we're working with. So some of the terminology that comes up with graphing is increasing and decreasing functions. We say that a function is increasing if the values of y increase as the values of x increase. So that means as you move from left to right, so as the x values are going up, y is also going up, as you can see from the graph on the left. So as you go from left to right, your function goes in the upward direction, means that. Similarly, we say that a function is decreasing if the values of y decrease as the values of x increase. So here, as we move from left to right, as the x values go up from 0 to 1 to 2 to 3, the y values go down. So you can see what a decreasing function looks like as you move from left to right. We also talk about concavity. Concavity is the shape of a graph and how it's curved. A graph is said to be concave up if it bends up as you look from left to right. A graph that is concave up looks like a cup that will hold water. A graph is said to be concave down if the graph bends down as you look from left to right. Often, concave down graphs look like a hill. So this is just some of the terminology that comes with graphs that we'll be discussing further along in the chapter. We can look at a graph and now use our vocabulary to talk about this graph using increasing, decreasing, and concavity types of terms so that when we look at it, we're all on the same page. If you look at the graph in front of you, this graph will be increasing when x is between -1 and 2, that's where it's going up, and also between 6 and 9. The graph is decreasing when x is between 2 and 6. We can also say this graph is concave up from x equals 4 to x equals 9. That's where it makes that cup shape look. We can say this graph is concave down when x is between -1 and 4, because this is where it's rounded down like a hill. Now would be a good time to try the homework for Chapter 1, Section 3.